Hi everyone, in this video we are transitioning away from energy and into a new topic of physics known as impulse and momentum. We are going to more or less quickly just define and see where these two things come from in this video. We will be further elaborating on both of these topics and applying them to problems in the future. So introducing two terms, impulse and momentum. First, the impulse equation. The impulse equation, what we call impulse, really comes from Newton's second law. So that's what I'm going to write out. If you remember Newton's second law, the net force acting on an object is equal to that object's mass times acceleration. Well, that means that F net is equal to m times delta v over t, acceleration being the change in velocity divided by time. Technically, it's delta t here, but remember, we'll always say that t naught is equal to 0, and that just makes our algebra a little neater, one less step, one less thing to have to include. Well, I could swing this t over to the other side, because it's in the denominator there. So that means that F net times t is equal to m times delta v, or net force times time is equal to mv minus mv naught, because of course delta v is equal to v minus v naught. This right here is what's known as the impulse equation. It's simply, really, a form of Newton's second law. Impulse by itself, impulse is abbreviated with the uppercase letter J. Normally, you're not going to use J in an equation, but J, impulse, I guess if you define it, it's how much net force there is multiplied by time, and therefore it's also this mv minus mv naught. So impulse, how we're going to use it, you're not really going to need this J. This is almost exclusively how we'll be using the impulse equation, which is stuff we've been using before: force, time, mass, and velocity. Okay, that's impulse. Now, oh my goodness, once again, as a physicist who's deriving equations, we just came across something interesting. The amount of total force acting on something multiplied by the amount of time it's acting causes a change in something. Here again, we have our two similar terms, and there's a difference. There's a change going on, going from one type to another type. That makes whatever these things are interesting, at least to a physicist. They are therefore given a name. This is where momentum comes from. All right, we see it pop up in this equation, this really just quantity that's changing when you have a net force and you have a time. So this is what's known as momentum. If I squeeze it in, I'll rewrite it down here in case you didn't have room. Momentum is really just the label given for the quantity that changes when you apply a net force and time. All right, this is known as lowercase p, p for momentum. So really, this is the impulse equation. That's all I have for part A. All right, technically the symbol for impulse is J, but this is pretty much how you'll always use the equation. And this is where the term momentum comes from. So let's just go through and then quickly define momentum. Really, the best definition is it's what changes when you have a net force and time. All right, now that definition has changed, it's tweaked, it's simplified, especially if you imagine physics where you're not doing a lot of math derivations. All right, so momentum P is a property of moving objects, yikes, that should be moving objects, based on their velocity and mass. Often if you go online or if you read certain textbooks, they'll say it's inertia in motion. That's adorable, whatever. It's the mass times the velocity. And again, it's given lowercase letter p as the symbol. Okay, p equals mv, super straightforward equation. Now, momentum is a vector. So we're transitioning back into vectors. We didn't worry about vectors too much during our study of energy. We do have to keep into account direction when we look at momentum. Okay, an object moving to the right might have a positive momentum. If it's moving to the left, it might have a negative momentum. Well, we're not really going to do it in this class. If you have something moving at some angle here, you could look at the momentum in the x direction and the momentum in the y direction, but that's a bit beyond the scope of what we're going to be doing, but you could. Lastly, the unit for momentum, well, it has to match the equation. This is mass, so it needs to be kilograms. This is V, has to be meters per second. So kilograms, meters per second. Momentum does not have any special unit. Just like a Newton is named for a kilogram meters per second squared. For momentum, it's simply kilograms meters per second. All right, this is the foundation of what we'll be doing for the next few lessons, building off of these two core ideas. Thanks for watching.